Hello and welcome to this video for Chemistry 30. In this video for electrochemistry, we are going to look in more detail at oxidation numbers. I've used this terminology before already in some of our reactions, and oxidation numbers simply could be understood as an ion charge. And so when you have a simple ion like copper 2+, its oxidation number is its ion charge 2+. And if you have an atom by itself, element in its atomic form, it's going to have an oxidation number of 0. But what about the elements in a neutral molecule or the elements in a polyatomic ion, the individual elements, right? Because in a neutral molecule, elements technically are not ions, they don't have ion charges. Now, why do I need to have a oxidation number or an ion charge? Because it tells me what's happening in my reaction, right? Because in electrochemistry, we have a transfer of electrons. That's what electrochemistry is studying, or redox reaction, a transfer of electrons. When electrons are being transferred, that changes the charge or the apparent charge of an element, okay? So instead of calling it ion charge, we're going to call it oxidation number, sometimes also called oxidation states. But the rule is, if the oxidation number of an element goes down during a reaction from its reactant to product form, it is undergoing a reduction reaction. And remember, we have our saying, Rallio the ogre. So if the oxidation number goes down, that element is acting as an oxidizing agent. It's gaining electrons, undergoing a reduction half reaction. If the oxidation number of an element increases from its reactant to product form, it instead is acting as a reducing agent. It is losing electrons and undergoing an oxidation half reaction. Okay? So in order for a redox reaction to take place, there has to be a change in oxidation number. One substance oxidation number has to go up, the other has to go down. So here's our rules for assigning oxidation numbers. And like I said, some of this we've already talked about. If you have an element or an atom in its element pure form, like copper solid, for example, or hydrogen gas, this is their elemental form, their oxidation number is 0. Okay? If I have a simple ion, like, again, copper by itself or in an ionic compound with a 2+ charge, its oxidation number is therefore 2+. We also know, generally, that group 1 ions all have a charge or oxidation number of +1, and group 2 ions all have a charge of +2 or an oxidation number of +2. So sodium, for example, is +1. Calcium is +2. That's basically all we know other than oxygen and hydrogen. Okay? Hydrogen, 99% of the time, is always +1. Unless it's bonded to a metal, then it's -1. And oxygen, 99% of the time, is -2, unless it's in something like hydrogen peroxide or sodium peroxide, some type of peroxide, then it's -1. But otherwise, it's always -2. Okay? So what that means is we know that hydrogen is always +1, oxygen is always -2, simple ions are their ion charge, and then everything else can change. But what we're going to do is look at the sum of all of the oxidation numbers and do a little bit of algebra to figure out what each element would have to add up to that sum. So when you have a compound, whether it's ionic or molecular, a compound, the sum is always going to be 0. When you have a polyatomic ion, the sum is always going to be its net charge. So for phosphates, it would add up to -3. The individual oxidation numbers are going to add up to -3. Okay? For magnesium oxide, they're going to add up to 0. So let's look at how we determine the oxidation numbers for elements that we don't know we're trying to find. Okay? When we do this, so let's say I have compound N2O. Okay? I write the individual oxidation numbers of the atoms on top and the sums on the bottom. So again, oxygen we know is always -2 unless it's in a peroxide. So this is not a peroxide. A peroxide is either hydrogen peroxide or the name, it would say it's something peroxide, for example. Okay, so basically hydrogen peroxide is really the one you have to look out for. If it's not, it's -2. Now there's only one oxygen in this molecule. So -2 times 1, the sum of all the oxygens is adding up to -2. Now this again is a compound. Compounds always are going to add up to a sum of 0. So that means I'm actually trying to solve for x up here. But I'm starting down here. I need to know what number will add to -2 to give me 0, and that would be +2, okay? But that is the sum of the oxidation numbers of all the nitrogens, and there's 2 nitrogens. So that means each nitrogen has to be +1, and that's the oxidation number of the nitrogen in N2O, okay? So I start with the sums on the bottom, figure out what they need to add to, and then because I had a 2 here, I had to take this 2 and divide by 2 to get each individual nitrogen, which was +1. Okay, very similar to what we would do back in Science 10 and Chem 20 when we have a multivalent metal, right? If I had CuCl2, for example, right? I would have said each chlorine is -1. There's 2 of them, so that means I have -2. So that means I need +2 because this has to, again, equal 0, right? So that means my copper as a multivalent metal has an ion charge of +2. This applies same process to oxidation numbers. So copper's oxidation number is +2. Okay? Now let's look at the next example, the nitrogen in nitrate. Now again, my oxygens I know are -2. So there's 3 of them, so 2 times 3 is -6. This ion has a net charge of -1. So I need a number that I can add to -6 that will give me -1. That's a +5. +5 and -6 will equal -1. Now there's only one nitrogen, so that one nitrogen will carry that entire oxidation number of +5. Now, if there was a 2 here, I again would have needed to divide by 2, and I would get a fraction, and it is possible to have a fraction, okay? It doesn't have to be a whole number. So notice how nitrogen, right? Nitrogen in one compound, its oxidation number is +1. In another compound is +5. So nitrogen and like other elements, the only elements we really know for sure are group 1 and group 2 metals. We know oxygen and hydrogen, and then everything else, every other element can have any oxidation number. Okay? So looking at a couple more examples, we're going to look at carbon in ethanol and carbon in glucose. Okay? Both of these are neutral or molecules where they have no net charge, right? They only have a net charge if they're a polyatomic ion. When they're a molecular or ionic compound, the net charge is 0. I know my hydrogens again are +1, and I know my oxygens -2. So I have +5 from those 5 hydrogens, -2 from these 1 oxygen, and +1 from that 1 hydrogen. So I have +6 and -2, so I need a -4 to add till that all equals 0. There's 2 carbons, so they are each -2. And then the last one, I have +1 again for my hydrogens and -2 for my oxygens, so +12 and -12 for the sums of those elements. That already equals 0, which means my carbon is actually going to be 0, and again it can. Okay, oxidation numbers can be any number, including fractions. Okay? So, why again this is important is because it tells us whether or not a redox reaction has happened or not. right? If I'm given a reaction and asked, is it a redox reaction, I'm going to assign oxidation numbers. Here my silver is 0. Sodium is a group 1 metal. It's in an ionic compound, so it carries its +1 charge. Now nitrate. Nitrate is staying nitrate on each side. So I don't need to look at the individual elements, because if nitrate is staying nitrate, it's obvious the nitrogens and oxygens are obviously staying the same. Okay? My sodium is in its atom form now, so it's 0, and my silver is in its ion form now, so it's +1. Okay? So this was a redox reaction. The silver went up and the sodium went down. So when that happens, that means again that we have a redox reaction. Now, if there is no change in oxidation number, like the following example, we have SO4 again on both sides. I don't need to look at each atom. I can just keep it as an entire polyatomic ion with an ion charge of 2+. My lead starts as 2+ and continues as 2+ because it's in an ionic compound. My potassium starts at 1+ and stays at 1+. So nothing is changing in oxidation number here. Okay? So what that means is that this is not a redox reaction. It's a chemical reaction, but not a redox reaction. It does not involve a transfer of electrons. Okay? Transfer of electrons are redox reactions. Notice how this reaction is single replacement, back to Chem 20 and Science 10, and this reaction is double replacement. That's kind of a hint for you as well. Single replacement is always going to be a redox, and double replacements, unless the ions are changing their charges, which usually they're not, they're just switching partners, that is not a redox reaction. So some examples where electron transfers or redox reactions happen in living systems are photosynthesis and cellular respiration. If you remember those reactions back from the thermochemistry unit, electron transfers are happening. Those are redox reactions. Same with some non-living systems like combustion, a hydrocarbon combustion reaction, bleaching, which is a type of composition reaction, and metallurgy, which is a type of decomposition reaction. Those also are redox reactions. Okay? So basically what I'm saying is all of the reaction types we learned about in Science 10 and Chem 20 are redox reactions except double replacement. So if you're given a question like this, I have double replacement, double replacement, double replacement. If you have time, obviously you should check and make sure the oxidation numbers are not changing. And right off the bat, we should be able to tell that the first one, there is a change in oxidation numbers. I'm starting with elements. This is a composition reaction. I'm starting with elements, so they start as 0, and they're turning into ions, forming an ionic compound. So the potassium increased and the bromide decreased. So A is your redox reaction. Now there's one last terminology that we need to do before we finish this lesson, and it is called disproportionation. Disproportionation will come up. It is when an element has undergone both oxidation and reduction in a reaction. Now, how can that happen? If we look at the oxygen in this first reaction, the decomposition of hydrogen peroxide, this is a common disproportionation reaction because oxygen in hydrogen peroxide, remember that was the exception, where the oxygen is -1. In every other compound, it's -2, and when it's by itself in its atom form, it's 0. So notice how the oxygen decreased in oxidation number when it formed water, and then it increased in number when it formed oxygen gas. Okay? So this means that the oxygen in hydrogen peroxide went under reduction and oxidation. Where the oxidation number goes down, that is my reduction. When the oxidation number goes up, that is my oxidation. Okay, oxidation and reduction processes. So that means the water, or the hydrogen peroxide, sorry, is acting as both the OA and the RA of the reaction. That's what disproportionation means. And we have the same thing happening in the next example. I have chlorine gas starting as 0. It's turning into this polyatomic ion, which adds up to -1. So the chlorine in this polyatomic ion is +1, and over here it's in its simple ion form, which is -1. So again, the same thing happened with my chlorine. My chlorine went through an increase in oxidation number, which would be an oxidation reaction, and a decrease in number, which would be a reduction half reaction. Okay, so disproportionation is when one element is both oxidized and reduced in a reaction. So it has to be in two products, and in each product, in one of them, the number has gone up, the oxidation number has gone down. Okay, so that is it, I believe, for this lesson. Thank you for watching.